Hi, folks, and welcome back to another thrilling installment of excitement on the DT Engineering YouTube channel, where we bring you the very best of content from the British Columbia Institute of Technology's Technology Teacher Education Program, where shop teachers go to learn to become shop teachers in BC. And this is the first lecture of my section of the course of TTED 4035, where we're going to be looking at printed circuit board design. And we're going to use one of the many available programs that do printed circuit board design. We're going to use Fusion 360 because we're using it for a number of different applications already, and because it's got printed circuit board design software built right into it. So I've got a few things to say before we get started, and then we're going to start out by designing the schematic for a Winky Blink, and then we're going to design the toner transfer printout for a printed circuit board design so that you can actually do the toner transfer, copy it on to a printed circuit board, etch away the material that you don't want, and have a printed circuit board ready to go for your class. Later on in the class, we're going to do more complex circuits. We're going to take a look at how this can be used to manage integrated circuits. We might even get into some surface mount components. And if time allows, we'll also take a look at how to export these files and send them off to a commercial manufacturer so that you can have your circuit boards manufactured and even get double-sided circuit boards and all that ready to go. But today we're going to look at the Winky Blink. And for those of you who aren't in my classes at BCIT but have had the misfortune of stumbling along this channel and are burrowing down a YouTube rabbit hole at the moment, a little bit about the Winky Blink. You can see it laid out on the circuit diagram right in front of you. And this circuit diagram is actually from the GP Vanier Tech program. And it was really cool when I printed it out and saw that this one had been prepared by Dawson Ross. Thank you, Dawson, former student of the and graduate alumni of the Technology Teacher Education Program at BCIT. Prepared this while teaching over in Courtney. So yeah, we actually do go out and we apply these things and we put them to good use in the classroom, helping kids to learn about some of the exciting world of technology out there. So anyway, we're going to keep this schematic open right over here on this screen as we go through with it. So if you're following along with the video, I suggest you find a schematic of the circuit. And if you're looking for it, it's not hard to find, tech.gpvanier.ca/WinkyBlink, right up there at the top of the page. And you can go there, you can bring it up on a window, or this is a really simple schematic. Take your pen and paper out and sketch it down right now, just so you remember what you're doing as we go along and we can follow it component by component. Now, one of the neat things about what we're going to do today is we're not only going to create this drawing, but we're going to use the logic that we create in this drawing to create this drawing over here. Now, it's one of the neat things about printed circuit board design software is most of your CAD design software is very literal. When you design something, you basically you're designing what you're going to get. I mean, there's no second layer of understanding or meaning going on there. If you draw a box, that's because you want to make a box. But in here, you're going to draw a resistor in the schematic, and the resistor you put on your board is going to look absolutely nothing like this. It's not going to be squiggly at all. This represents a concept that it's difficult for the electricity to get through that resistor right there. The resistor that you're actually going to put on there is going to look something like this over here. And the key part about it is that you're going to have two holes on the printed circuit board that you're going to drill through the circuit board so you can fit the leads for that resistor through there. And there's going to be two pieces of copper right there that are going to join together. And those pieces of copper aren't going to touch anything else on the circuit unless this schematic diagram says that they're supposed to contact, because on this schematic diagram you can see right here that this resistor right here, this side of it connects to this resistor and to the LED. So if we take a look over here, we'll see that our 220 ohm resistor comes out here and it connects to a 47 K ohm resistor, and then it comes over here and it connects to the positive side, the anode of the LED. Okay, so what we're going to do today is we're going to use Fusion 360. We're going to start by creating a schematic right in here. And when we do this, we're going to put in components, and the components are going to both have a logical symbol, but also a physical footprint that we're going to use for creating this design later on. And we'll develop this drawing first, and then use the parts that we place in here to create this drawing second. And what that lets us do is it lets us know that all of these traces are connected properly in accordance with the schematic diagram. Now, you screw up the schematic diagram and your printed circuit board is 100% going to have the exact same errors that you put into your schematic diagram. So getting the schematic correct is a really important part of your design. Why do we have two different parts to our drawings? This is intended to communicate to somebody who understands how to read a schematic how the circuit works and what it does. This is designed for manufacturing. And you can put your LEDs in different places. You can put your resistors in different places. You can use different sizes of transistors, different sizes of resistors. You can do all sorts of different things on there. But we're going to take a look and we're going to see how we can put this together and make the most of what we've got. Okay, now before I get to that part, there's always a before. Before I get to that part, I have to take you on, a couple of references here. First of all, if you've forgotten what a Winky Blink is, or you haven't been in my classes and you don't know what a Winky Blink is, there is a video that I've got right here. It's on my channel. You can take a look, called Breadboarding the Winky Blink right here. And this will come through there. And you'll have like this, what direction is he? That guy over there talking about a Winky Blink. So anyway, if you've forgotten what a Winky Blink is, that talks about breadboarding it. And if you haven't had a chance to check out the video in my TTD 4035 playlist, oh my God, you think I'm going to say like and share or something like that. No, please don't. This is just a way of communicating lecture information to you. Um, but anyway, I also have a lecture here on what the different terminologies are on here. And this video is called Printed Circuit Board Terminology for the Home Hobby Educational Circuit Board Designer. I've got a PowerPoint of it up on our Desire to Learn page, our learning management system for the course. And so you can, if you're in the class, you can take a look in there. If not, look on my channel for this video right here, and it takes you through, and we spend some time talking. Actually, for my videos, it's only 23 minutes. You watch that at 150% speed, you'll be done before you know it. Talking about what jumpers, headers, mounting holes, components are, what the different layers on a circuit board are, the top documentation, the bottom copper, how we manufacture our boards, why we're making some of the design choices that we make, how to make a trace follow a net. Okay, so some of these terminologies you're going to use while we're using Fusion 360, but you're going to see we're going to have to go in and we're going to have to adjust annular rings. And later on, we'll be using dip chips. Okay, sometimes you might also see a single inline package that we're going to use. We'll talk about the pitch between the holes. Okay, we'll talk about the diameter of a drill hole and the size of and type of a pad. Okay, and we'll definitely be talking about the trace or track widths that we use to create around here so that you can create a trace that is both easy to manufacture for you and your students and also capable of carrying enough electricity to make things happen. We'll talk about multi-sided circuit boards and some of the design considerations if you go there. So anyway, that's a little bit of pre-understanding that might help you with what's going on in here. If you get stuck partway through where I'm using some jargon and you don't get it, you can go back and take a look at the Winky Blink video to understand how the Winky Blink works, or you can take a look at the circuit board terminology to understand some of the terminology that we're using in here. Okay, and I'm running this on Fusion 360 on BCIT's installed version of Fusion 360 via Apps Anywhere. I do have a local version of Fusion 360 installed on my computer. It should look pretty much the same, but I thought since we're going to be doing this on lab computers and running the Apps Anywhere version, I'm going to run this on the Apps Anywhere version. Anyway, before we get to all of that, I have to take you on a side detour because my mind has been blown by Chat GPT once again. Chat GPT has written poetry for me. It has composed a flamenco song for my wife who dances flamenco. It's composed this song for her about me sitting in the husband chairs of the stores of Seville waiting for her to buy fabric. And then it not just translated it, but it just recreated the entire song in Spanish so she could actually sing it at Spanish class. So anyway, I came into Chat GPT when I got home today because she was doing some cooking and she had some fish out. She's a really good cook, so I wanted to make sure that whenever she's cooking, and she's like, whatever you want, dear, we'll get it. She said, could you ask Chat GPT for a recipe for a Persian style fish dish? And so I went through and had this chat, and I like to chat with Chat GPT like it's an actual person. I always figure that when the robots take over the world, maybe they'll spare me because I was nice to the first AI. Um, so anyway, it recommended a fish dish for us that looked really good, but we didn't have tamarinds. So I said, we don't have tamarinds, but we do have preserved sumac and preserved lemons. So it updated the recipe and came out with a Persian style fish dish that she cooked up. She liked that recipe. I printed it out and it was amazing. Oh my God, it was so good. But by that point, I was logged into Chat GPT and I was thinking about this morning's class where we did our Arduino Symphony Orchestra project, another video that I've got on my YouTube channel, but basically where we were using Arduinos to make sound. And I said, I've heard ChatGPT can do some programming. So I asked ChatGPT, let's do some programming. And it asks, what language am I working in? I'm using an Arduino Uno with the Arduino IDE. I have a speaker connected to pin 9. Great, what kind of project? I'd like to write some code to play the opening notes of Imperial March from Star Wars. Within 30 seconds, it comes in and it starts chewing out this code right here. Now, I know there's code out on the internet that already does this, and it's probably putting it together. And to be honest, I haven't tested this code. But doesn't this look like the stuff we were downloading and looking at today? There is an array with the notes. There's an array with the duration for each notes. It does its setup. It sets the pin to an output. It runs a void loop. It goes through. It takes a look at the notes. It takes a look at the duration and plays the note and the duration. And then it carries on. About the only thing that I'd critique this program for is that it immediately starts back in and starts playing it again later on. I may try it out later on. But look at this. Not only does it give me the code, but it explains a few things about how it works, as if ChatGPT actually understood what it was doing. Now know we know that it doesn't. I mean, it's just a really advanced search engine that goes out and takes together little bits and pieces and all puts them together in some logical way. And you have to know what you're looking for in order to correct that. But I thought, oh, well, let's see what happens. How would I do that in Python for a Raspberry Pi Pico with a speaker on pin 9? And I was expecting something really similar, but I wasn't expecting this code in the middle. It actually went and used a very advanced feature of the Raspberry Pi Pico that's kind of unique to the Raspberry Pi Pico, called the programmable I/O pin, and it went through and it did that, and I was kind of blown away. So again, I compliment it because hey, I want the record to show that I'm nice to ChatGPT. Um, and it does seem to respond well to that. I don't know why people keep getting these mad artificial intelligences. And so I thought, well, if it knows how to program, maybe it knows electronic circuits. And yes, it definitely has knowledge of electronic circuits. And I described the Winky Blink. Okay, now this is a key term about the Winky Blink that helps things understand what's going on. The technical term for a Winky Blink is a monostable multivibrator. And if you want to get giggles, use that with your grade 10 class. Okay. Yes. So anyway, I am familiar with the Winky Blink circuits. It's a simple monostable multivibrator, blah, blah, blah. It echoes some of the question that I gave it. And then it tries sketching this out. And I'm not entirely sold on the caliber of its ASCII art for drawing schematic diagrams. but you can bet somewhere there is somebody working on code to turn that into a proper schematic diagram. However, it's got a great description of how the entire circuit works. And then I'm like, okay, Chat GPT, this time I got, yeah, I'm creating a video showing how to create this printed circuit board in Fusion 360. And I'd like a set of instructions on how to do that. Well, we're going to follow those instructions and see how it goes. Create a new schematic in Fusion 360, open Fusion 360, click on the electronics workspace. It's good. This is what I was running through in my head that I was going to go through and show you guys how to do. Chat GPT's laying it out for me right here. We'll see how close it is as we go through. However, one of the real challenges that we're going to run into is that when we bring the parts in, I thought, aha, does it know which parts to use? Can you recommend any specific libraries or parts to use in step 2 of your instructions? Because step 2, it just said add components. Okay, it was very generic about which components, so I wanted specific instructions, and it picked the libraries that I was planning on using and the part names that I was planning to using. But one of the things that you'll see in here is that it used a surface mount component. See that SMD right in there? Surface mount components are really tiny. You don't drill holes through the board for them. We may do some surface mount work later this year. Definitely we'll do some next year. But I didn't want to get into that in our first exercise. In fact, I specifically want you to avoid the surface mount components. So we take a look at that. And I said, that's pretty impressive, but I'd like to use through hole only components, please, because those are the components that we drill a hole through. Those are our standard resistors and capacitors that we use all the time. So anyways, I ask it to change the instructions, and sure thing, here are some recommended through-hole components for the Winky Blink circuit. This is commonly used NPN transistor, so we're going to try using those parts. And it tells us about the parts, but it didn't give me the names in the Fusion 360 parts library. So here it tells me which libraries to look in and what parts to use. It also suggests a ceramic capacitor. Ceramic capacitors won't go up to 10 microfarads very easily. We want a 10 microfarad capacitor at least, maybe a little bit bigger in our Winky Blink circuit. So, oh yeah, the first thing I asked it about 9-volt battery pack. It recommended a couple different batteries. We'll have to see how they use. And then I asked it to suggest an electrolytic capacitor instead. So it recommended this from the passive capacitors library. So we'll see what that looks like. So I've been pretty impressed with Chat GPT so far. So just before I went in and started the rest of the video, I was just going to say, thank you, Chat GPT. We'll try some of those instructions. But before we do, can you make a humorous limerick about the Winky Blink circuit? Okay, it's been too long. Obviously, my connection's timed out right here. We'll give it one more chance to regenerate that response. Oh no, here we go. Are we getting a? I think I'm timed out right now. Um, so anyway, somewhere in there, the humorous limerick about the Winky Blink circuit created by Chat GPT is yet to come. But if you haven't played with Chat GPT, it can probably give you the instructions that you need for solving a problem, and it may be quicker than going to the help file for some circuits. Well, let's see how this works. Create a new schematic in Fusion 360. Open Fusion 360, click on the electronics workspace, and create a new schematic by clicking on File, New, Electronics Schematic. Here we go. In to Fusion 360. Boom. Okay, so we are in the design workspace right now. We said to go file, and then we want new. We've got something new up right in there. Where are we looking for this workspace? We need to get into electronics. design, generate, animation, simulation, manufacturer, drawing, file, new, oh, just a minute, did that wrong. Close that last one. It was right in there. Come into here, file, new electronics design. Its instruction wasn't that great. File, new electronics design, comes up right in here. Okay, and this is a slightly different looking design right in here. So we're going to come in here and we are going to create a new schematic. Okay, and this is just dragging a little bit because I'm running this over a VPN into BCIT, so I can actually use the BCIT version of this in Apps Anywhere. Okay, there we go, and I've got a new schematic coming together right in there. Let's see what Chat GPT says as our second step. So file, new, yeah, that's not quite the latest instructions. Now you do have to keep in mind Chat GPT is only up to date on data from the, I think 2021, 2022 is when they started to finalize and lock down the artificial intelligence engine. So any changes to Fusion 360 since then will have updated it. Add components. Add the necessary components to the schematic by clicking on the Add component and selecting the appropriate component from the library. Okay, so what components does it recommend? Um, part 2N, sure, transistor. And then we want to find the library that has it. So we want a 2N3904 transistors BJT library. Okay, well, let's see if we can find the transistors BJT library and add something in here. So here's our schematic in here, and we're just going to add the components for right now. And if you come along the top right here, where are we here? Things have changed around a little bit. Um, place component. Okay, so instead of add component now, it's called place component. You still hit the A button to do it. Okay, and now you've got some libraries in right here that you can choose. And this was said it was going to be in the transistors BJT. Let's hope we can find that in right there. If we can't, well, we'll have to look for it the old-fashioned way. QRS transistors. Well, there's a transistors component in there, and variant PNP. We want a PNP transistor, and there's a whole bunch of different transistors coming in here, and none of the ones that we want are right in there. So one of the things about using any electronics design program or EDA program is managing your libraries and keeping track of the parts, because there are thousands and thousands of parts. There might only be hundreds and hundreds of symbols, but each symbol can represent a whole bunch of different physical parts. You can have a through-hole part, a surface mount part, a 5-watt resistor, a 10-watt resistor, or a 20, yeah, okay, well, massive resistors, as well as our little quarter-watt resistors, all represented by the same resistor symbol on there. So finding both the part that you want and the footprint can be sometimes a little bit challenging. Let's see in here, are there any other libraries that it was talking about? Oh, there might be more transistors down here. Oh, here's a transistor PNP library. And oh, Chat GPT might have been onto something. Let's just move that over so we can see it a little. We want a 2N3904. There's some 2Ns in there. Let's sort by component name right there. 2N3906, that's the NPN version. 2N, well, where is our 2N3906 looks about right. Where is our 2N3904? Now, to be fair, we can do some searching for that, and we can filter for 2N39. Not in there. Where did Chat GPT say to look? I think it got it wrong. Transistors underscore BJT library, 2N3904. There's a 3906. And when I look at my libraries, let's go all libraries. I'm just not seeing anything come up in there. Okay, so let's look in all libraries for an NPN transistor. So if we type in transistor, if we just type in NPN right here, now it's going to go through and it's going to take a look at all of our libraries. So make sure that you've got all libraries and NPN selected right here. And now we want to take a look at some of the different sizes right in here. And this one is a TO92 package. This is the size and shape that we want. TO92 is the name of the package that we want. That's the physical case for the part. But this one's collector base emitter. We want EBC, emitter base collector. This one's EBC, but it's a TO18 package, not what we want. Let's try this one in here. TO92, eat big cookie package right in here. Okay, so the package that we want is in the transistor library, and the name that we want is TO92 EBC. And when you look at it down here at the bottom of the screen, you should see your symbol for the transistor. You should see your pinout for the transistor. Should go 321 on there, and then you should see the actual shape of the transistor. So it looks like the part that we want to put in there. And now what you can do is you can take that and you can just take that part and say, yes, that's what we want. And we should be able to come over here and just by clicking on the screen, we should be able to add that component. There we go. I just had to click on that, pick it up. And so you should be able to pick it up. You should see this. You can drag it along anywhere. And yeah, we're just going to put one right here. We're going to move it later on. We're going to adjust some of the writing on it. We're not worried too much, but we need two transistors. And one of them, I'm just going to mirror and flip it around this way because that's how our design looks down here, right? We've got a transistor down right here, and we've got a transistor over here, and that's why you keep your schematic open, is when you start adding your parts. We're only going to add two, Q1 and Q2. We've got our transistors in there, and ChatGPT is not looking quite so hot anymore. It was looking really good till we actually started listening to what it says. Well, let's see what it recommends for the LED, Passives LED library, LED 5mm THT. Okay, passives. Is there a passives library in here? I guess we could, if we wanted, to save ourselves some hunting around. What did ChatGPT recommend for that name? LED 5mm. Let's just come back up here. Let's leave all of our libraries selected. And let's just type in LED. Oh, lots of LEDs. Space 5mm. Were those capital M's? Nothing in there. Okay. LED 5mm. No, nothing coming up like that. Not so impressed there, ChatGPT, or you're not doing so great on that one. However, we can pull a few things up here. Now, I want a little bit more space for this, so I'm actually just going to get rid of this section on the side of the screen by clicking up here and going Hide Data Panel. That gets me a little more space to work with and should make it easier to see what we're doing right in here. So all libraries, and I am just going to bring this up a little bit. Right on here, you can click and move and drag some of this around. There we go. And so LED, now we have to come in here and find which LED do we want? Adafruit is a manufacturer of parts, and they usually have pretty good things going on here. This LED, that's an RGB LED. We don't necessarily want that. There's a bunch of headers in there, connections, displays. Oh my goodness. Where are we going to find chip flat, chip round? Okay, that's getting a little bit closer. Maybe there's other packages. You can see these are all surface mounts. They've got red pads on them. We don't necessarily want those. We're looking down here. SparkFun's another manufacturer that might have something good. Those are encoders. LED chip. Nope. LED cube. Oh, that's something that I made. Um, we'll take a look at making our own components and parts later on. There's an RGB LED. There's a 7-segment LED. There's an LED library in here. This has a WS2812, which is a programmable LED. We'll look at our programming class. Let's see what happens if I just go 5mm. 5mm, because it's a 5mm diameter LED. Here's what's going on in here. Are any of these parts going to work? No. And this is kind of like sorting through your parts bin to find the part that you want to use for the project. Now, another way to go about doing this is to say we're looking at all of our libraries right now. Like I said, some libraries are better than others. So let's narrow this down a little bit and let's find one that's probably going to work out pretty well. And what we're going to find is, where did that Adafruit library go to? Let's just look in our Adafruit library, and in Adafruit there's an LED and it says 5mm right on there. There's our footprint that we're looking for. So there you go. Pick the Adafruit um, library and then search within Adafruit for a 5mm component. You'll get this one right here. Check and make sure you've got the LED symbol down right here and something that looks like your LED in the footprint. We're not going to worry too much about that drawing. That's just a 3D model. So long as we've got a good footprint and a good schematic, we'll take that and we'll bring that in here and we'll drag that in. And there we go. We'll put one, yeah, I don't know, about right there. And one right there. Okay, so Chat GPT going 0 for 2 basically on the parts recommendations. Glad to say it got the recipe right. It did a good job on the recipe, maybe a little bit better than it's doing right on here. Let's see what's it recommend for a resistor. Resistor in Passives Resistors library. Well, let's see what we can find. Is there a Passives Resistors? I don't see that as one of my stock libraries, I don't think. Battery holder, audio devices. No, let's just stay in the Adafruit library and let's just search for R, E. Ah, and here is a part that's going to work really nicely. Now this says R-US. Okay, there's European and American symbols, European and American symbols. This is the American symbol for a resistor with the zigzaggy lines right on here. The European symbol is just a box right on there. Both of them are going to work just fine. This looks like our resistor part right in here, and we're going to need 4 of them. Now, I know that some of them are going to have different values, but we can change those values up later on. So when we know that both our symbol looks right and our footprint looks right, specifically that we've got no red in there, because the red is representing top layer components, which means that you've got a surface mount part. We're seeing green. Green is good. You're ready to go. Just take that and drag it in here. And now you can see it's not in the right orientation that we want, so we can rotate that around just by clicking right up there, and we can put a couple in right in there. I think one of them comes in about right here. Now let's put two of them, one here, one here. You'll see me glance down at my schematic right in there. I've kept that up for you, but it's always a good idea when you're designing this to have a sketch of your schematic open. In fact, anytime I'm doing CAD, I kind of like to have a sketch of what I'm drawing open, ready to go right in there. And now we're done. Okay, oh, there we go. So 4 resistors, kind of in that orientation right in there, is looking pretty good. Now we've got to add a couple of capacitors. And so let's take a look in that Adafruit library again for CAP. And here we've got C-US. Okay, again, that's the American symbol for a capacitor. The European symbol will tend to have a flat line along the bottom more. But now we want to take a look in here and find a hole pattern that looks about like our capacitor footprint. You recall our capacitors are kind of cylindrical. So I'm just coming past all this and I'm seeing some axial capacitors that lie flat in there. I'm seeing a bunch of surface mount stuff. There was some through-hole stuff earlier on, but I'm not really happy with that. And part of the reason is because this is just generic capacitors. We also have C-pole, which is, you don't need to worry that you don't know this going in. It took me a while to figure out as well. This is your polarized capacitor library. So for our aluminum electrolytics and things like that that are polarized and have one positive end and one negative end, we can come in here and click on that. You can see that for one symbol, there's a whole bunch of different parts, surface mount parts and through-hole parts that could represent our capacitors. And now we've got some different sizes right on here. So the sizes can represent the spacing between the leads and the diameter of the part. And we don't have to get this perfect, although it'd be nice to get the spacing between the leads just about right. You can see here that this one has same spacing between the leads. Part gets a little bit bigger. I think this one's going to be right. Now, it's not a panic if we get it wrong. We can go back and change it later. But if you get it right now, it's going to save us steps later on. So I think this E10-20 is going to do a nice job for us right here. Okay, so I'm going to pick that part up right there, drag it onto the board, and there I've got a capacitor. And to rotate it around, I can just click up there, and I'll put one in, sort of pointing in that direction, and then I'll mirror that, put one pointing in that direction. Right in here, we can arrange the rest of that later on, and I can click done right on there right now. Okay, so we've gone through and we've got the transistors, we've got the capacitors, we've got the LEDs, we've got the resistors, all 4 of them right in there. Now we want to wrap it up by adding a 9-volt battery, and then we also want to add a diode right in here just to make sure that we don't hook anything up backwards. You stay right there. All right, let's come on in here, and we've been having good luck in this library. Let's just try D for diode, I, diode. What have we got for a diode? Okay, don't go with the first one that you see. That's got red on it. That means stop. It's surface mount. We might use surface mount diodes later on. There's a through-hole one. That one, it's a little bit skinny relative to what we're used to using. Let's just see if there's any other options. Nope, that's our through-hole diode in here. That one will probably do the trick just fine. Okay, so make sure you've got something that looks like a diode here, something that looks like it should look like on your board right here, and then bring it in here, and we'll drop it in right here. And this one's got the diode pointing in that direction. It's always hard to figure out where I am on the camera. Right, my camera's up there. It's got it. Anyway, I've got one camera right down over here, and then the big one looking at me right up here, so I get confused sometimes. So I'm just going to mirror that, point it in this direction, and I'm done. Okay, and now we need a battery. Let's see. That one's not necessarily how I'd hook up an AA battery onto the board. Um, let's see what we've got for a 9 volt. Sometimes you'll find it under 9 volt. Nope, that's not clearing it up. I think there is a part called 9 volt. Let's just go to all libraries, plus 9 volt supply. Now some of these you'll see don't actually have a footprint. We're going to use them later on as logical symbols. So don't pick the parts that don't have a footprint. We're looking for a footprint like this, AB9V. Okay, that's a pretty good part right there. And you can come in here and take a look, and you can see that we've got 2 holes right on here that we're going to be able to drill into the board, and we'll be able to hook up our battery to that. Okay, so let's just take AB9V, bring it onto the board right there. Now I'm rotating it around by clicking on there's the right mouse button right on there. So every time I hit the right mouse button, I get a rotation. That's perfectly fine. We want the positive pointing up. Let's put that right over there. And there's our AB9V, and we're done. We now have all the parts on the board that we need in order to make this board. Okay, so what we're going to do is we're going to connect them together, and we connect them together by creating nets. Okay, so this is where you want to have your schematic open, and if I come down here, I click on the end of that net, and I come over here, bang, and I connect that together. All right, now, may as well do a neat job of it now. We can tidy it up later on. This is a form of drafting. And as you know, one of the things that we try to do in drafting is to communicate designs clearly and neatly. And there are sets of rules that we have to follow. So we're going to follow those rules. I'll talk about them a little bit as we go, and I'll definitely talk about them when I come to assess your work. Okay. So there we go. Those are hooked together with nets. And that one's going to come down right in there. And this one comes down right in here. And this capacitor, now let's take a look at our diagram. The one that comes over here to the collector of the transistor, that's the positive side, comes right in there. So this one is going to come over here to the collector of the transistor. That one's going to come right in there. And let me just say I'm done for a moment. I'm going to pick this part up here and just move it up there. I'm going to move this part right up here, that part right up there. Give myself a little bit more space just to pick up on these things. And oh, it doesn't like it because I'm trying to pick that up and I'm not clicking on. So I can click on the X right there and I can move that part. I want to move. There's a secret spot on each of these that you have to click in order to move. You can see on the resistors, the X is right in the middle. And on on the LEDs, I can't quite see that secret X spot. Should be in here somewhere. There we go. Nope. I highlight it and then click move. How did I move that last one so easy? Where is that secret X spot? There we go. Ah, that's why it was hard to find. It's right where those two parts join, right in there. Okay, so I've moved all that up. For my capacitor, that spot seems to be right there. It's a good spot to grab that one. Okay, and then we're going to come down here and we're going to go back to adding our nets in when we've got things aligned a little better right there. So this is going to join right in there. It's going to come across and join right in there. This one's going to join right to there. You'll know that you've got to join because that dot will appear right in there. Alrighty. This side right here is going to come down and going to click right here to get it to run across like that. This one's going to come down and join right there. Okay, how are we doing so far? That all looks like a Winky Blink to me thus far. I'm going to come over and I'm going to join my two emitters together. Going to join the diode right in there. We get that little dot saying that we've got a good connection. Then I'm going to connect it over to the battery right there. And yeah, right now, that's actually looking like a Winky Blink. That's done up pretty easily. Okay, now we want to add some information to this circuit. So for this resistor right in here, I can click on it. Oh, I'm going to right click on that resistor and I am going to change my values. So when I right click on there and I come in and I change my values, my new value for R1 is going to be 220 R. And we use R for ohms because good luck finding the ohms key on your keyboard. And we'll do the same right here now. If it's not showing up, if it's giving you that bling, that means you haven't found that secret X spot. You might need to zoom in a little bit, right click, okay, and value and 220R. Okay, there we go. Now those are looking pretty nice. Now what I like to do, if I've got the space to do it, is take these numbers right here. No, hit escape because I'm done in there. And on that little gray corner right in there, you see I can move that and I can right click to change the angle that it's at. And let's just make this easier for whoever has to read this by putting R1 up there and R2 right there. And let's put the values horizontally so that they're easier to read. Okay, R3 we can put right in there. We got lots of space on this circuit, and we can right click and we can say, let's come in here and change the value of R3, and this one suggests a value of 47K or 47,000 ohms. Okay, and we can take that value, oh, hit escape if you keep getting that because you're in the wrong mode. There we go, R3 is 47K right there. R4 can go right there, and we can change the value of that to 47K. Hit escape. There we go. We can take LED 1, put it in a nice, easy to read spot. LED 2. Now, one of the things you'll notice that I am never, ever, ever doing is I am never, ever, ever putting the name right over top of a component or right over top of one of the nets. That would look ugly and it would lead to confusion, and we'll redesign the circuit before we have to do that because that would just be wrong. Okay, it's like those ancient Assyrian breadboarding rules that I teach you. Um, I'm a little bit tongue-in-cheek about that, but it matters. Okay, it makes a difference between look like you know what you're doing and not knowing what you're doing. We could say 10UF or just 10U. Actually, we should probably use the small u right in here because it's micro. Okay, and we're not going to leave it looking like that. That's ugly. We're going to take that 10U, we're going to rotate it around, put it right in there, and C1, we'll put right down here, and we'll change the value for C1 value, and we'll set that up to 10U as well. We'll bring that down, escape, put that right in there. We can leave this at NPN right here if you want, but it's obvious it's an NPN transistor because the arrow is not pointing in. So maybe we come in here and change that. Let's see if we can change a value in there. Instead of it saying NPN, let's say 3904. The full name of it is a 2N3904, but we're just going to come in here and change that to click on the orange dot to get the value and 3904. There we go. That's set up in there. D1's a generic diode. Um, all of those parts are laid out horizontally. Uh, escape. We'll just rotate that over here. And for some reason, it's used G1 for the battery. I'm not going to worry too much about that, but I am going to change. There's the place for that value. No, do you want to change it anyway? No, I'm not going to worry about that. AB9V is fine. It's got the 9 volts in there for us. I'm reasonably happy with that. Okay, so there's a schematic. The only thing that's missing right now is a little bit of information about the schematic itself. And so in order to do that, we're going to come into Document, and we're going to hit the text button, and we're going to find a nice place to say Winky Blink, J. Brett, March 2023. Oh, we're going to try that again, just a minute. I got a little too excited about clicking that I was done. Okay, we have to come in here and find a spot that's going to look good on our diagram. Maybe it just goes right in there down at the bottom. We can click done. Okay, now anytime you print that schematic, it will have the name on it, which is really useful for helping people figure out what it is. It's got the name of the designer on it, which is helpful for finding help. You know, can say, oh, Jay Brett, I should ask, you know, is there a Jay Brett and a Winky Blink that I can ask about? And it's also important for giving credit, just like I did for Dawson for having his design up on the internet in such a neat and available and easy to access format. Alrighty, so now what I'm going to do is I'm going to come over here and I'm going to hit save. Probably should have been doing this as we went along, but I was just having so much fun. Now it's going to ask you what location do you want to save it in. So I've got a whole bunch of different projects open right here. Admin project default. I'm probably not going to put in my syringe excavator. I'll probably put it in my test projects, and I am going to call this Winky 2023 because I've made a few versions of the Winky before. Okay, now I've got the schematic drawn, and if you want, you know, find me in class. If you're doing this in class, have me come and take a look at this. If you want to get a printout of that, okay, how do we get this? Print it out so we can take a look at it, hand it out to your class or something like that. Just come up to this command bar at the top and type in print. Somewhere there is a print button that will allow you to do that. This window right here will pop up, and you know, you can scale it up to fill the page if you want. 1.5x. There you go. So it fills the page a little bit better. Maybe I even want 1.7 on there. Okay. Now we can do all these things like mirror things and scale things because schematics are just ideas. Okay. But if you're when you start working on the printed circuit board, don't mirror things and don't scale things because they're designed exactly the size they're going to be. But on schematic, go ahead, play with it all you want. If you want it all black, you can make it all black. You know, you can rotate it on the page, take advantage of portrait and landscape, whatever you want. You don't have to print a copy of it right now, but a great way to hand it in is to use Microsoft Print to PDF and print it out to PDF. And that way, when it comes time to hand it in, you can just upload the PDF of your schematic. Okay, so go ahead and print that out and make sure you've got a saved copy of a nice, neat, tidy um, schematic of a Winky Blink with all the part numbers in place. Okay, time for a coffee. Or if you're doing this at 10 o'clock at night, maybe just a glass of water. Um, so let's take a look right in here. Now, when we created this file, we actually created a project file. And the project file is where we're going to hold our schematic that you can see in here, but we're also going to create a board file from that. Okay. And now that we've got this in here and we've got all our parts with the correct footprints in here, we should be able to come along and just say create a new PCB. Now this is running a little bit slow because I'm running it through the VPN and running it at BCIT. So there we go. Okay, so it's come up right in here and it's given me a new printed circuit board. And here are all my parts. And wow, looking at that, those capacitors came in bigger than I had imagined them coming in. They're not supposed to be much bigger than the LEDs. Okay, so I'm not really happy about that. Let's just drag everything right there and just drag it onto our board right there. And I think we want to go back and we want to change the absolutely ridiculous size of some of those two capacitors. They're definitely too big. So now we've got the different things open up at the top right here. Um, you know what? Just before we do, I'm just going to save that just because. And there we go. Oh, it saved as PCB. I should have gone File, Save As. I should have said Winky 2023, and then I could add PCB. Remember not to put dots or anything in there. That always messes up naming criteria if you start putting dots in there. Okay, now if you get this line right up in here that says schematic may be out of sync, let's just take a look in here and come back to our project file. And yeah, it should all be in sync. We'll update it anyway. We need to come in here and we need to make some changes. So come back to your schematic right in here, and on that capacitor, right click on it, and we are going to go and see if we can change the package. Okay, and our package was a little bit too big. So, oh, and actually when we look at it this way, no wonder that is showing us 10 millimeters across. That's a little too big. Here's one that looks better. That's less than 5 millimeters across. So we actually want the E 1.8-4 right in there. So we'll click OK. And then on this one right up here, we'll do the same thing. And we'll go package. We're just going to change that package down to E 1.8-4. Okay, it even has a dimension, diameter 4 millimeter. That's about what we're looking for. And I can hit save now. And now if I come back to my printed circuit board diagram, okay, try opening the associated electronics design first. Let's close that. There is a way to update all of this in here, but I think my best bet is to close that. And then come back to my project file. And let's open this one up right here. And this should open up, updated with the latest parts in it, because we use our schematic to drive what's going on. Okay, it gets one warning. Board and schematic are not consistent. no forward backwards annotation will be performed. Now that's a really important warning that we need to stay on top of. If you see that, don't just click on it and let it go away. It says use the ERC command, more info. Okay. Use the ERC to find differences and resolve them. So this is the error rule checker. We're going to talk about that a little bit more in just a moment. And then you can see it tells us what all the errors are. And then we're just going to go and we're going to say synchronize. And the synchronizer comes in right here. And devices C1, devices C2. And we should be able to just go ahead and run that. I think it should update everything sensibly. There we go. And now we've got the right size footprints on here. Okay, this diagram stayed the same. This one changed. And then you can just hit save so that they stay together right on here. And all of our parts look right about there. Now, if you want to copy Dawson's design right here, that works out okay. We've got other designs that you can do. Let's see on here. His looks a little bit different. He's got the battery up at the top, so you can bring that around right there. Now you see that there's little yellow lines following it around. Those little lines are called the air wires. And Dawson's got his positive on this side of the circuit. Not a problem right there. We're just going to see what we can do to get those air wires all sorted out. And then he's got a couple of 220 ohm resistors. Now watch what you're clicking on when you pick that up, okay? Because depending what you get, you might get the whole resistor. That's perfect. That's kind of what we want. Bring that over there. It doesn't have to be very far apart, just outside the component. But sometimes if you click on the gray part, you see I didn't get the resistor, I just got the part number. We can move those later on, but if you get the part itself, you'll move the part and the number together. So pay attention and make sure that you get the thing that you actually want to get when you go to move it. You can't just get in there and start moving things around too rapidly. And then he's got a 47K resistor right in there. Now, if you follow the air wire, you can see that air wire says this eventually wants to connect to this side of this LED right down here. And so in Dawson's design, he's kind of got it set up like so, I believe. There we go. That comes in and connects there. Oh, interesting. On that side, he's got the round side down at the bottom. And I see what he's doing. He's doing something a little bit different. Well, you can follow that design if you want. I see how he's doing it right in there. Bring that right in there and leave room. You've got a 47K resistor, and the 47K resistor you want in there is probably this one, because you can see it does interesting things with those air wires. All it's doing is it's showing you that this part needs to be connected to that part, okay? And as you move this around, there become simpler ways for them to be connected. It still says this is connected to here, is connected to there. But just depending on your geometry, it will find different ways to illustrate that concept. So there we go. We're going to put that one in right in there. Maybe move that in right about like so. And then he's got a 47K that comes in right here. I'm using my right mouse button to click on that and rotate it. And R4, going to bring in right about like so. Now I could put them closer together if I wanted to. I'm not totally concerned about getting everything super close together right at this point. Then he's got this one hooked in right here. Okay, then he's got a couple of capacitors hanging out up in his design right up in here. Now you don't have to follow this at all, okay? You can come up with your own circuit design, but if you're doing this for the first time and you're looking for something to guide you, I can tell you Dawson's a pretty clever guy and you wouldn't do wrong to follow what he's done. And you can put one right in there, something like that. And then there's a transistor that you can come down here. And he's kind of stuffed his transistors down in at the bottom, about like so. And let's see which ones he got going where. This one's going to want to connect right in there. Where does he have that connection going? Eat big. The base runs around to the positive on that one. So which one's got its base coming off the positive? That's coming right there. I think he's got them hooked up this way and this way. And he's got the diode coming in right about like so. Okay. So now this might work, it might not work out well. I think he's got it figured out pretty well, but we'll give it a shot and we'll see what happens. Now, don't follow the air wires directly. Okay, we're going to do some routing in here. And before we start filling in the air wires, replacing our nets, the logical links right in here that are represented by the yellow air wires with tracks or traces, the physical copper that's going to be going in there, we're going to come in here and we're going to set some rules up in here, okay? So we have to come in here to the rules DRC. And in the design rules, we have to set up our design rules. And when you click on that, you get a little window that looks like this. And here's our Fusion 360 design rules. And we need to change a few things up. Because right now this has both a top and a bottom layer on it. And we don't necessarily need that top layer. And let's see, what does it give us? A one layer option? It doesn't give us a one layer option. Um, let's see right in here. I'm just going to hit Control Z, take me back on what I did. I didn't want two layers. Oh, well, I've got two layer stack in here. Okay, so what have we got in here for our layers to look at? On the top, we've got our top solder mask layer, our top silk screen layer, our top surface finish layer, and there's our top layer. And I don't really need a top layer. This is all going to be on the bottom layer. Our bottom layer is going to be located right down here. And so I am going to set our bottom layer. Okay, I want to make sure that I've got some unique colors in here. Let's see if I can open a preset file. Does it have any useful preset files? I don't see any in there. I'm just going to cancel that. This is something that's changed just a little bit in terms of their colors. Typically, when you come in here, we should have the top being in one color, and I believe the bottom is usually in blue. So let's come in here and we want to change the bottom layer. I'm going to click cancel on that and hit DRC again. Layer stack. Yeah, the top and the bottom layer should definitely look different from each other. And there should be a way to edit this up. And it looks like they've changed where that goes. Material type, it's a signal. There's our thickness. And I should be able to click on that and change it. Half a sec. Okay, I don't think that's going to be a big problem now that I look at it. They've changed the colors in the design rule check from what I remember, but the colors and the layers over here are still red and blue. So when we do our drawing, it's going to come out all right. Yeah, just seeing that threw me for a stock. So this is going to be a 2-layer board, but we're only going to use the bottom layer, so it's going to be a 1-layer board. Now, one of the things that we do need to do when we're in design rule check is we need to give ourselves some space in between our components. And we can do space between a couple of different things, between 2 different wires or 2 different routings on the board. We're going to go, in this case, and we're going to go 25 mils, or 25 thousandths of an inch for space. And we're going to give ourselves 25 thousandths of an inch of space all the way across right here. We're not going to worry about the vias though, because vias are something that only come into play when you do a 2-layer board. Okay, so that's between different signals on there. I'm not going to worry about this line either. That's again for more sophisticated boards. The distance between objects, we're going to leave it at about 40 thousandths of an inch. Okay, the sizes, the minimum size of the trace that we're going to put in there, we're going to bump that up also to about 25 thousandths of an inch. Okay, and our annular rings, okay, now as I mentioned earlier, the annular rings are these green spots right there. That's how much copper is going to be left behind after we drill out the hole in the middle for that component. We can bump the minimum size of that up, and let's take that up to 15 for our pads right in there. And if you just click on apply, you'll notice that our capacitor pads suddenly got a little bit bigger. That way, when a student drills those out, they'll have just a little bit more meat left on the bottom of the board, and a little less likely to be left with nothing to solder to if their etch doesn't go perfectly, or if their drilling is a little over enthusiastic. Shapes, we don't have to worry about. That's for surface mount stuff. Supply, again, that's a little more advanced. And so we just click apply, and there we go. And we can close this window. Just make sure you hit apply first, and make sure you got those slightly bigger pads right on there. You can see that we did get a little red line in here indicating that those are close together. So our cost for making them a little bit bigger is that they end up a little closer together. But that's all right. Okay, now you can see right now we're starting out on the top. So before we start doing anything else, we want to change layers. I'm going to use my hand to hit the keypad and hit L. Oh, that should have switched layers for me. I'm just going to switch over to the bottom layer anyway. And now you can see it's nice and blue up there. Okay, excellent. So now I'm going to come over here to our design. And now that we've got our design rule check set up, we can go route manual, and we can start figuring out how to connect these. Here's a nice easy connection from right there. You get that rewarding bing from right there to right there. Okay, so those ones connect right in there. Now, in Dawson's design, where does he go next off there? Well, then he'll take these ones right here and connect to right there, and right over to there. And those ones all join together. Now, if you keep looking at your schematic, double check back to your schematic, make sure that those ones are supposed to be connected together. Okay. Then this one right here is supposed to connect to right there. Okay. And then this one right in here is supposed to connect right to in there. Okay, now this is where things start to get interesting, because now we've got lines crossing over top of other lines, and that can be a bit of a pain in the butt. So let's see right on here. What's you got going on in here? That emitter comes around right to there. So he's got these ones hooked together right in here. This is interesting. Usually I work off one of my own circuit board designs, and so that emitter, that emitter should be connected to that emitter right there. I'm going to Control Z what I did right there. Get rid of that. I think what happened was I clicked on the wrong yellow line right in here. I wanted to click on this yellow line right here, so I'm going to route manual. And I've got that line right there. There is a problem with these two transistors. Can you see what the problem is with those transistors? This is why it's important to follow along, is sometimes even you think all the parts are right, but there's a problem right in here. And the problem is that if we were to take our NPN transistor and put it in here, and this is a 3904, looking at the NPN transistor from the front, we should have our emitter, our base, and our collector. And this should be our emitter, our base, and our collector. But in this circuit, those ones are showing up as my emitters because when you look at the schematic, the only things that are hooked together are those two emitters. So I think, although we went out of our way to choose an EBC part, I think Fusion 360 kind of messed that up and gave us a bad part in the library. So we can't always assume every part in our library is going to be perfect. However, we can fix that because it's been mirrored. So like I said, we never mirror our parts in here unless they come in already pre-mirrored. Okay, now we actually have to fix this part. We don't want the numbers mirrored. Turn the mirroring off right there. And now when we look at this part from the top, we're looking down on top of our board from above. The traces that we're seeing are actually back behind the screen. Okay, those are on the back of your screen. Those are underneath the entire circuit board. Those are on the bottom copper layer. Our components are on the top. And now when we look at our transistor from right here, we should go emitter, base, collector, eat, big, cookie. And here's our emitters, the two that are joined together. And those should join together about like so into the diode about like so. Now try to keep your lines so they look nice and neat and organized. Okay, part of the idea of making the board is to make it look good. And Fusion 360 will chamfer edges for you and do all sorts of things like that to help you look good, just like that. But you've got to let it do its thing. And you've got to help it and guide it sometimes a little bit too. Okay, there we go. Transistors repaired. And then our LEDs come down right in there. And then let's see, what's this one going to have to hook up to in here? Now this gets a little bit tricky because this one wants to come down and connect to that collector. So you can see Dawson routes that around out over here and then brings it down right in here like so. And he's got a little bit of an edge right here because his transistor is set up with three parts all in a row. And you can see right in here, when I try to write this part out this way, it's not gonna do it for me. It'll come out this way and it'll come around right here. So we can't really follow his routing because we're giving ourselves a bit more space and we have a slightly different part. Now that's not a problem so long as it's electrically connected right in here. We've got a lovely path that it can follow right in there. All we're going to do is we're going to hit escape so we can move things. I'm going to move this over and down a little bit like so. And now this part right here, I'm going to come back to route manual. And this part, instead of routing around down at the bottom like Dawson did it, we're going to be able to bring it up, tuck it in around right here. And bring it in that way. That worked out pretty good. So that transistor is all hooked up, except we need to get this part right over here and have that route down into there. He wrote that part around right there. He has it hooked up to the capacitor on that side. He brings it emitter, base, the collector comes right around. Oh, interesting. He's got that coming to that capacitor over there. So this part he brings down and he routes right into here. Like that. This part right up here, you can see we're trying to get in to this part right over here. So it would like to find a path. Now Fusion 360 is pretty good. You can see when I push around like that, it tries to find a path to get over where it needs to go, but it's having a heck of a time finding a way to get around down to over there and right into that part. Oh, that's going to be a tricky one. This design might not work out okay for us. We'll have to try a few other things. I've got one more to route right in here. This one's going to come down in here. It's got a hard time getting around that part. Hard time getting around that part. Ooh, there's some trickiness going on in here. So maybe this isn't going to work so good with that running right through here. Maybe we've got another way that we can get around doing some of that. Okay, let's take this right here. Now, if I come in here and I click on that, I can tell it that I want to rip it up. Okay, and we've got rework over here, but what we've really got is rip up. Where am I looking for? Route, quick route, modify. Rip up is the term that I want for this section right in here. To polygon. Well, I'm going to try deleting that. Okay, good. It left the airline behind. Just a minute. Control Z that. Now you'll see that when I did that, it made the air wire disappear. Be very careful to not let that happen. You've got to watch where that air wire goes because this right here still needs to know that it needs to connect to right here. Now it may redraw the line somewhere else. Okay, it still drew that line down to there. That's perfectly acceptable. Okay, but when you delete a part right in there, make sure it doesn't get rid of that air wire. Okay, those ones need to connect right there. Let's try bringing, play around with the location of a few different parts in here. And maybe we'll try routing this one through down here first. Oh, that one's routing in pretty nicely. Happy sound right in there. Okay, now that creates space for this one to come down here, up and around right here. That one gets in right there. And now we're left with one nasty little one right Indigo right here. How is that going to get through from right there to right there? Tricky. Okay, so this works a lot better when you've got three transistors with three prongs in a row, like this one does right down here. You see those are all in a line and spaced out a bit more. This is actually how this actually makes manufacturing a little bit easier. And in my previous video, this is the type of transistors that I use. So I used a layout that I knew was really good as our layout. We're going to have to pull some of this up and do a little bit of reroute. We know that we can route this. We've done it before. Stop and see if you can come up with a solution for that. I'm going to see if I can come up with a solution, but I'm going to pause the video while I do. Let's see. Yeah. Oh, right. I'm producing an educational video right now. Um, I was having trouble doing some routing in there. I was surprised it wasn't working right. So I took a little break and went and played Flow Free. And it's a simple little connect the dots game. You can get it for your phone. It's got a few different rules. You have to fill in all the spaces while you're doing your routing around here. But you can see you've got dots and you've got lines to connect them with, and you can't overlap. And it's a lot like the puzzle you're doing in Fusion 360. Um, so having taken a little mental break and played a little bit of flow free, I came back in here and I rearranged some of my boards. And let's see, I can come in here and I can do some manual routing. And I can go bing, bing, bing. And I can click on done. And maybe you can see some changes that I made into that circuit that are going to make it work. Okay, now how do I know that I'm done? How do I know that it actually works? Well, remember we set up some design rule check rules earlier, and we've got rules DRC over here. You can come back over here to DRC. Okay, click on that DRC button, and you can go check. And it tells you what your errors are. And if you click on each of the errors, well, that was one that we already took a look at. When we increased the diameter of our annular rings, we ended up with things getting close to each other. Clearance, where's another clearance error? And another clearance error right there. So those are errors that we already knew about, and so that's no errors whatsoever. So we can click on approve for each of those errors, and now all of our errors are gone. Just make sure you know what you're doing when you click on that, and make sure your schematic's right, and you should be good. Okay, so we can close that off. This circuit board, if we got the schematic right, is going to work for us. We've got some nice spacings in here for our students. Now, we can do some things to make it a little bit nicer for them to create just yet. Okay. One of those things is that we should probably put a little name on it somewhere. So come back to document, and just as we did before, we've got the ability to, oh, we don't want the annotate in there. We want to draw, and we want to create some text. And we're going to say Winky J. Brett. Actually, just looking at the space that I have, I'm going to say Winky Blink J. Brett 2023. Okay, and now that's just a little bit big to tap into there because we're going to put this onto the copper layer. We can change that size down a little bit. And I think that's going to fit right on there. So now when you make a board, Okay, we can click done right on there. There's a little bit of space right on there. And then we can come in here and we can grab this edge of the board. Try to keep it nice and rectangular as you do that. Bring it right into here. Bring it right into here, about like so. Maybe I got a little too tight on that edge. And now that shrinks our printed circuit board size down. I left a little space in each corner so that we can come in here and under our design, we can place a hole, okay? A non-plated through hole, and we can come in and we can put that hole right in here. Now, what size hole do we want? We want that to be 1/8 of an inch is going to be 125 thousandths of an inch. So we want it to be a 125 thou hole. So we can put one right there. Okay. One right there. And maybe one right down in here if you want. Try and line these ones up so that they're nice and square. The tools for doing this aren't quite as good as in regular Fusion 360, but we can say done, hit escape. We've got our name on it. Brought the edges in a little bit right there so we're not wasting a lot of space. About like so. Other things that are really nice on here is we've got our uh, lines routed really neatly. You can see the name of each net on these. Remember, a net is the logical connection. The trace or the track, our copper line, is the physical manifestation of that net. Now, you can see on here that a lot of our numbers are really hard to read. That's because the bottom layer is turned on. Let's just turn that off for a moment and see if we can arrange some of these things on the top so that they're a little easier to see when we print them out. Okay, there's LED 2. Here's LED 1. Let's get our documentation layer looking nice. 10U right there. Where's the name for that capacitor? Where did we leave C2 behind? There's C1 sitting over here. And C1. Now, technically, because this is the documentation layer, we don't need to have the values on them. They'll appear on the schematic. We do need to have the C1 and the C2. And I'm not sure where C1 got to. Here's R1. I'm going to put that right up there. G1 for the AB9V might come up here. Now keep in mind, these aren't on the copper layer, they're on the top documentation layer. They're not getting in anybody's way. Okay, R3 is going to be right here. And maybe I don't even want to worry about the 47K on here. So I'm just going to, I should be able to delete that, get rid of that, delete. Okay, delete, delete, delete the 47K. Don't delete the part numbers though. We want to take them and arrange them neatly so that we can see where our one's going to be. Remember, the more precise you can make this and the easier you can make it to read, the fewer questions you're going to get from your students and the more success that they're going to have. And believe me, after teaching electronics for a while, you appreciate it when your students have success the first time out more often than they appreciate it, in fact, because it's quite a challenge to get it to happen. Oh, there's D1. That's really tiny right down there. I'm not going to worry too much about that. Oh, there we go. We can maybe change the size of that up from 16 mil. There we go, up to 50 milliliters, so or 50 thousandths of an inch, so people can see that. Just trying to figure out where did C1 go. Let's go name, C2. Okay, where is C2 supposed to be displayed? I can come in here and go properties, name C2. It should be showing. Well, I'm not going to suffer you with that. If you've got that problem happening to you, we'll take a look at your board and we'll fix it up. But try to get those all arranged right in there. And then when you turn the bottom layer back on, it's going to look like a bit of a hodgepodge. But remember, when you manufacture this board, you're not going to see those copper lines. You're only going to see them on the bottom. And then you're going to see this all up on the top. You may not even print that layer. That might just be something that you print later on. Okay, so we've got thick enough lines over here to manufacture. They're spaced well enough. We don't have super long lengths where they're all close together. See here, I've got two lines right next to each other for a way. If I come down here and I pick this, and let me just hit escape for a moment. If I take that and I just move that down a little bit, I want to move both parts of it down a little bit. Let me try moving that right there. And I just give myself that little bit of extra space right in there, and maybe a little bit of extra space right there since I've got the space on the board. That makes it easier for the etchant to get in there and remove the copper from right in there. Okay, so make this board as easy as you can to make, because chances are you're going to make quite a few of them, and then you're going to have to troubleshoot them if they don't work. So give yourself plenty of space between those gaps right in there. Try not to have long runs running next to each other, and use something like a 25 thousandth of an inch routing so it comes through right on there. So anyway, thank you to Dawson over in Vancouver Island for sharing his designs with us down here. I see what you did there, Dawson. Nice work on that. We're going to double check here. Our emitters both go off to the diode. We got that worked out. Our collectors both come up to the negative sides of the LEDs. And you've got yourself a printed circuit board. Oh, why is this text in backwards or mirror image? Because that's on the bottom of the board. That's coming up from behind the board, and that's going to be on the copper layer, so that as soon as you make this board and etch it, your name will be forever bonded to the board in infamy. Okay, for getting this out of here and actually doing something with it, what you're going to do is you're going to be able to go print. Actually, before we do that, we only want to print the bottom. Well, let's see what happens if we try print. We might be able to tell it that we only want to print the bottom copper layer in here. Nope, we have to come in here, turn off the documentation layer. So come in here and you can actually turn off all the layers. Okay, and then just turn on the bottom copper. Okay, and turn on the pads. And yeah, I think that's about all that you need for making your circuit board. And then come in here and type print. Okay. Oh, just a minute. We need one more thing. There should be dimension. Should give us the board outline. And print. There we go. And your print dialog should come up. It should look something like that. Okay, remember to make sure your scale is set to 1. Okay, because you put all that time into getting all of your parts the exact correct size. Okay, we can print that to PDF. We don't need to mirror this. It's already been mirrored. If you're doing the top layer, you do need to mirror it. We are going to print it black. We're going to make sure it's solid. We're going to add a little caption to the bottom so it says what it is. You can print that to PDF and you can hand that in, or you can print it to a copier or to a laser printer, and then you can do toner transfer from there with toner transfer paper. Okay, let's just click OK. And where do I want to save that? Give it a place to save it to. And Winky 2023. And that should flash up and show me what it looks like. Come on, Acrobat, where are you? Let's see, there we go, we're going again. That's what it should come out looking like in Acrobat. And then you can print that out at 1:1 scale for toner transfer. There's your through-hole mounts. There's all your annular rings for your different components. If you wanted the top side of the board, um, where's Fusion gone now? If you wanted the top side of the board, you'd just turn everything back on here, okay? Um, and then you could turn off that bottom layer, and then you could print out the top layer right there, and that would give you the top documentation layer so that somebody could know which component was which and be able to tie them all together. Okay, make sure you save that when you're done. Okay, and call me over to have a look at your schematic and your circuit board and the fact that they're both stored together in a project saved to your Fusion 360 file. With that, you should be able to start winking and blinking. How long was that? Hour 41? Not bad, considering we had a side detour into Chat GPT. Hopefully that works out, and you've got your first circuit board designed in Fusion 360. Good night.